Okay, now I am recording. So, I'll be introducing the guest of today, Dr. Benjamin Reid, who will take us through the dynamics of the ionosphere and also the thermosphere. Here's a quick biography of our guest. Dr. Ben is a space physicist at the University of Birmingham, England, United States. I'm sorry, United Kingdom. He's an associate professor with the Space, Environment, and Radio Engineering group, and also a faculty advisor for Birmingham Students Satellite Program. Dr. Ben obtained his PhD from the prestigious University of New Brunswick in Canada and worked on the modeling of space environments, especially the ionosphere. He's obtained his bachelor degree from the same university and has held several honors. In addition to modeling, Dr. Ben is highly skilled in data simulation, space weather, GNSS, statistical programming, and Monte Carlo simulation. Outside the academia, he's passionate about leadership and extending access to space science in the global south and other underserved regions. Please join me to welcome Dr. Ben. And Dr. Ben, feel free now to start your presentation.
All right, thank you. I think it's the nicest introduction I've ever gotten. Uh, yeah, so I guess the goal of the next sort of two presentations here. The first one is going to focus on the ionosphere and also the thermosphere, because to understand, the changes that we see in the ionosphere, we kind of need to understand what's being ionized. And then in the second part, we're going to talk a little bit more about the high latitude ionosphere specifically, and then ionosphere magnetosphere coupling, because that's really important for understanding storms. And part of what we're doing in this program is, after you go and learn about all of the different kinds of instruments, it's going to be interesting to look at the differences that we see under storm conditions and under sort of nominal conditions. So that's why I've structured this the way that we're going to look at. So at first, it's going to look like nothing to do with storms. But everything in this first talk is going to come up later on in order for us to understand the changes that we see. So we're going to talk a little bit about the thermosphere and its dynamics. We often think about space and at those altitude ranges as being a vacuum, but of course it's not. And there's a lot of interesting, chemistry and things that happen there. And then we're going to talk about the ionosphere and just do a basic overview of what the ionosphere is, why it looks the way that it looks, and, what kind of processes govern it at different altitude ranges. So, the thermosphere. An important thing that comes up a lot when we're talking about atmospheres in general is this idea of a scale height. Right. And what a scale height is it is telling you how fast your pressure or your number density is decreasing with altitude. And it's a number that's going to keep popping up in equations whenever you're doing anything with the atmosphere or the ionosphere. So I'd just like to introduce it here at the beginning. And it comes from this idea of hydrostatic balance. So if you have a parcel of air in a column of an atmosphere, right, it has to be balanced by the pressure gradient. So you have a difference in pressure below it and the top of it, and that has to, through buoyancy, carry that parcel of air there. And so we get this number called the scale height, which is, you have Boltzmann's constant and the temperature, you have the mass of the gas, and you have the strength of gravity at, whatever altitude the gas is at. So you can see, right, as things change, if the temperature of the gas increases, the scale height increases, right? So hotter gas decreases in pressure more slowly, if that makes sense. Likewise, heavier gases have shorter scale heights. So the heavier an element of gas is, the faster it drops off as you increase in altitude. And if you make some assumptions, you say, we'll assume the temperature is the same at all altitudes. You get this really nice exponential profile that is a pretty good, I'm not going to say very good, but a basic assumption. If you want to model what an atmosphere looks like, it looks like an exponential decay. So, this is a nice isothermal formula, and we'll see this pop up in a few other places in this first lecture. But this other one is generally always true if it's in hydrostatic balance. This is the more complete one. And you can see if you pick different scale heights, and they're all at this sort of zero reference point. If you have a 200-kilometer scale height, it drops off very slowly. For a short scale height, it drops off very quickly. So, yeah. So part of where this comes up is the atmosphere is divided into a bunch of layers. And, this is the dividing line between these layers is determined by temperature profile. And so you've probably heard of some of these, especially the stratosphere is often the one that comes up the most. But the lowest one where we live is the troposphere. Right? Then you have the stratosphere above that, which is, where if you're in an airplane, you probably aren't right now, but, commercial air flight is in the stratosphere. Then above that, you have the mesosphere, where you have things like this is where meteors tend to be combusting. There's a lot of really interesting chemistry that goes on there. And then above that, you have the thermosphere. And these are all defined by transitions in temperature, right? Through the troposphere, your temperature gets colder as you go up. Then through the stratosphere, it begins getting warmer with altitude until you get to the stratopause. Then with altitude, it gets colder again through the mesosphere. And then the coldest part of the atmosphere is right at the mesopause. And then it begins getting much hotter very quickly. Which is why the thermosphere, which is what we're talking about now, is called that, because it's the hottest one. So the lower atmosphere is still important. We won't focus on it too much, but you can get coupling from the lower atmosphere upward through gravity waves and tides and things like this. So it's just important to keep in mind that there is energy transfer between all of these layers. Generally, things go from the ground upwards rather than up down. But they are coupled together. They don't behave completely independently. We won't worry about why the atmosphere has the structure. The answer is complicated radiative transfer things, which I'm not an expert in, so I'm not going to talk about them. But what is important, right? So we're on kind of a log scale now, is the temperature goes from the mesopause and increases rapidly until it reaches kind of a plateau. And if you remember from that scale height before, your scale height also depends on the weight of the species. So below this level called the turbopause, everything gets mixed together through turbulent processes. But once you go above that, and it's just about at the limit of the mesopause, then all of the different gases start to behave independently. They're not getting mixed together anymore. And so because they all have different masses, they decay away at different rates. So you can see, right, in the lower atmosphere, helium and hydrogen are quite rare. But once you go above, 1,000 kilometers or so, because they're so much lighter, they become the most common constituent now, right? And something like monoatomic oxygen basically doesn't exist in the lower atmosphere. But you can see it has quite a complicated profile. And then there's a region in the atmosphere where it is the dominant species. So as you go up or down in altitude, you get a different composition, and then this will change the chemistry and the ionization properties and everything else that we'll see later on. And when we start talking about storms, right, storms can produce bulk changes in the thermosphere, which is transporting these things up and down. And so you start changing the chemistry at different altitude layers, and this is where this will come up later. But the most important thing to remember is the temperature increases as you go up in altitude, and the composition changes depending on where you are. Right. And this is just the same thing I said, but I forgot I actually wrote it on the slide. So I'm sure you'll be able to have these slides afterwards. So, if you don't remember what I said, at least the words are here. And this is just a quick thing to show gravity waves. We're not going to worry about it too much. I mostly just really like this picture. So you have a large convective thunderstorm here. And that's a lot of air moving up quickly, and it creates these gravity waves like ripples on a pond that you can see in the clouds. But we won't really worry about those. The other thing that's important about the thermosphere is wind. So, the sun heats the atmosphere. Um, of course, it only really does this on the day side because that's where the sun is. But then all of that air, when you heat it, is at a higher pressure and it wants to expand, it wants to move outward. And so this drives, the wind systems that we have. And that wind will drag plasma along with it. It will do all of these other things, as it goes from the day side to the night side. And this is where we get, ionosphere thermosphere coupling. But that is our quick crash course on just what the thermosphere is, right? This is what is being ionized when we have the ionosphere. So, what is the ionosphere? So, it is a partially ionized plasma in the upper atmosphere. So, it is embedded in that thermosphere. Most of the atoms, molecules up there are not ionized. So, the ion component is a minority component up there. As opposed to something farther up, like in the plasmasphere or in the solar wind, basically everything is an ion. Down in the ionosphere, most particles are still neutral. So it ranges from about 70 kilometers to 2,000-ish, depending on who you're talking to. The lower part of it is in something we call photochemical equilibrium, and we'll talk about that a little bit more. And then above about 250 kilometers, it's diffusion dominated, which we'll also talk about. And it is organized into some distinct layers. So at the very bottom, you have the D region, which you basically can't even see on this plot. Then above that, we have the E region, which is produced photochemically in the F1 region. And then we have the F2 region during the day. And these two different levels correspond to solar maximum and solar minimum. These red lines are what the profile looks like at night. So you can see the E region, the F1 region disappear away. F1 region completely gone. The E region still persists a little bit, but that F region is still there. Sorry about that. My son is a little upset about something, it seems.
We cannot hear. It's too small.
Okay, great. I guess the microphones are doing their job.
No, your voice is this at the center, and don't worry about that.
Okay. Perfect. So, by law, every single talk about the ionosphere needs to include this image. I don't know why, but it is a very good image because it makes ionospheric physics look very impressive. Because it just shows all of the different kinds of processes that are going on. And if we wanted to talk about everything in this image, it would take an entire semester. But the important thing and the reason why everyone uses it is that it's complicated, right? You have the sun coming in, but you have magnetospheric convection, you have precipitation and gravity waves and field-aligned currents and ULF waves, and all of these things are all influencing the ionosphere at different times and in different regions. So that's always one thing to keep in mind, is that the ionosphere is just complicated. There's a lot going on, and it's connected to systems that are also complicated. All right. So one of the most fundamental things, I guess, right, is this continuity equation is really nice. So it's pretty straightforward. It is the rate of change of just how many ions or electrons you have is the gradient of that concentration with the wind. It's just how is that plasma moving, right? And then you have how much plasma is being produced where you are and how much plasma is being lost where you are. And the ionosphere will be in a balance of these things. Right. So between transport, production, and loss, and then different parts of this are dominant in different regions, right? Those different layers that we talked about. So the D region, we won't talk about too much. It's low down. It's very complicated, especially chemically. It's being produced by X-rays, cosmic rays, solar energetic protons on occasion. Because the neutral density is so high, if you're doing radio propagation studies, the D region is where most of your absorption happens. So even though the electron density is very low, we care about it because it absorbs our radio waves very strongly. But we won't talk about it too much more. So the E region is a little bit higher up. Generally, it's around 110-ish kilometers, but the whole region is a little bit wider. It corresponds to the peak of photoionization of molecular oxygen. So it has high collision rates. So that transport term in the continuity equation isn't as important, right? If an ion is created, it's going to collide with something in less than a second. So there isn't enough time to move the plasma around very quickly. It's constantly being generated through ionization and then being destroyed through chemical processes. And because of that collision rate, it's the most electrically conductive layer, which we'll talk about a little bit more when we talk about storms. But it's down here at the bottom, and these are sort of typical electron densities. The F1 layer is another photoionization peak of nitrogen and monatomic oxygen. It's not always present. It's only ever present during the day. And depending on diffusion and things, it can get occluded by the F2 layer. It can end up vanishing. So, right, it's easy to predict what altitude it will be at and what density it will have. It is hard to predict whether it actually exists as a separate layer or ledge, or if it just kind of gets absorbed into the F2 layer. But it's generally pretty well behaved. And then we have the F2 layer. So it's a bit different. Everything else we talked about before is a peak in photoionization. But the F2 layer is different. It is produced by transport of ions. So it's where we have the highest plasma density, even though we're not creating any plasma there, really. It is plasma that is diffusing upwards from the lower levels, and also plasma that's diffusing downward from the plasmasphere. And the lifetimes of the species get so long. This is why we have an F2 layer all the time, is that the plasma diffuses up and it just sticks around all day and all night. And so you always have plasma. But because it's diffusion dominated, it depends very strongly on those thermospheric winds for reasons that we'll talk about. So if those winds are variable and uncertain, which they are, the F2 layer is variable and uncertain. Perfect. So with that little bit of background, we'll talk about, I mentioned earlier solar maximum and solar minimum. So I don't know if this has been covered very much yet, but I'll just talk about it briefly. So the sun goes through this cycle of 11 years or so, where it will have very active periods and then very quiet periods. So when the sunspot number is high, when the radio flux is high, you have more ultraviolet radiation coming from the sun, and so you have more ionization on Earth. And you also have more more complicated sunspots, so you have more CMEs and flares and everything that makes space weather weathery, right? So this influences ionization rates through the UV, and also it changes the probability of getting geomagnetic storms. So whenever you're looking at an event, it's very important to know where it falls in this cycle. Right? And different neutral species are susceptible to being photoionized by different frequencies. And so solar activity, this is just here to show, this is a model of solar flux in the ultraviolet. The red is what the flux is at solar maximum. Blue is at solar minimum. So you can see there's a very big difference between the two of them, right? How much ionizing radiation exists. And then, of course, this will have secondary effects through how much the thermosphere is being heated and everything else. So just to say, the solar cycle matters when you're talking about the ionosphere. Doing for time. Not too bad. Okay. So photoionization. So we're going to, with this one, assume this nice isothermal atmosphere, and we're going to assume for this demonstration that we only have one species. There's only monoatomic oxygen or only nitrogen, or we're going to ignore the fact that we have different gases. And we're going to assume monochromatic ionizing radiation. So we're going to say there's only one wavelength of light that's coming in, just to get a simple idea of what a photoionization peak should look like. Right? So the photon flux at any given altitude is just found by integrating this. So you have a cross section here. You have your element of your distance, your number density, which we get from this isothermal assumption, and the flux, right? So it's just a simple equation. And you can go through the process of working this out, but essentially what you get is what's called the Chapman production function. So this Chapman layer, this Chapman function gets talked about a lot when you're doing ionospheric modeling because it comes from this photoionization curve. And even though the ionosphere, as we talked about, is a lot more complicated than just where photoionization is happening, especially for the E and F1 layers, they do, it is photoionization dominated. They do kind of look like just this idealized Chapman function. But the important thing to know is, right, it's sort of shorter, it's steeper on the bottom than the top. And it depends on the angle of the sun. So if the sun is right overhead, you get this 0-degree curve, right? There's zero angle between local zenith and the sun. And then as the sun gets shallower, the curve gets smaller, right? The peak gets smaller and it becomes higher in altitude, right? So if you ignored everything else and you just use this simple assumption, you get an ionosphere that, at the start of the day is quite high up and not as strong. And then the layer gets lower and stronger throughout the day. And then until you hit noon, and then after noon, it decreases again. Right? And that is broadly what the ionosphere looks like. So if you stripped everything else away and just did this photoionization, it predicts, at least on large scales, kind of what you would expect to see. As the sun is more overhead, that ionization is stronger. Of course, if you take the full spectrum, you say we do actually have multiple gases, we do have multiple wavelengths of light, and it's not that hard in a computer to just do that full calculation numerically. You would get something like this. So this black line here is the total photoionization rate. You can see we have a nice peak here corresponding to the E region. We have another nice peak here, which is our F1 region. And the species are different for both of them, right? We have oxygen as our peak down here in the E region. We have nitrogen as our peak in the F1 region. And then we have some other species here, monoatomic oxygen and monoatomic nitrogen, but they're minor species, but they still matter. All right, and then this is just what the equivalent profile would be. This is a model called MSIS. That's quite helpful if you need neutral densities. So just to say, but like that's still, if we go back and look at that Chapman, right? This is for a very, very simplified case. And you can see, right, we have all the species, everything now. That still really looks like a Chapman layer. So if you need to do something, it's still useful, even though a computer can do this easily now. So I guess the next thing to talk about is, all right, so we can make an ion, right? We have the UV come in, it makes an ion. What happens to it now, right? We're still not worrying about transport, but there are different kinds of reactions that it can do. So there's direct recombination, which is sort of the opposite of ionization. You have an ion species, you have an electron, they recombine and release, a photon. But the cross section for that is very small. That's a very slow process. The more common one is dissociative recombination, right? Which is you have a molecular ion, right? So direct recombination can be anything, especially atoms, right? A molecular ion plus an electron is much easier, right? It splits the molecule apart and both of the components go flying off in different directions. This is a very fast process. And then we have charge exchange. So you can have something like an atom, monoatomic oxygen, and this could be something like, to pick a random example, nitrous oxide or molecular nitrogen, right? N2. I wrote it down here a little wrong. This is supposed to be a plus, but essentially it transfers the ionization from one molecule to another. Um, so what ends up happening is that, especially lower down, you have, you get an ionized species. It exchanges its charge with a molecule, and then that molecule can break up very quickly. And so this it's just to know that different processes are dominant in different areas, but we're not going to worry about it too much. Now a much bigger equation, which we're going to mostly ignore. So this is, the momentum equation. So if you hear people talk about, the um, continuity and momentum equations as sort of being the fluid equations of the ionosphere, right? This is just what they look like for your own interest. And it's just a sum of all of the forces on it, right? So you have the pressure term here, right? You have a pressure gradient force. You have gravity force, which, is a tensor here. Is it a tensor? It's a vector quantity at the very least. Um, right. You have your electromagnetic forces, and you have neutral winds here. And then these are collisions. So different species will exchange momentum between each other, right? And this intuitively makes sense, and this is very important for understanding storms later on. Which is, if you have, say, one ion moving in one direction, right, they will be colliding with other ions. And so you can't just push all of your oxygen in one direction and not expect them to start dragging other things with them, right? Or very importantly, if you have a current in the ionosphere, right? If you have a bunch of ions that are moving in one direction, they're going to drag the neutral winds with them. They're going to collide with those neutral ions and drag them along. And so any change in temperature, any change in momentum in one species is going to get communicated to all of the other species in your fluid through collisions. So these collision rates are very important. And so different terms of this, right, dominate in different regimes. And I keep hammering this home, but it's very important for understanding the ionosphere, is that between the E layer and the F2 layer, you have very different regimes of collisions, very different important terms, right? They almost behave like different fluids. The really key thing that we're going to see is that the plasma diffuses most easily along field lines, right? And I'm sure that this has been talked about in other parts of space weather because it's always true. If you have a charged particle, that charged particle wants to follow the magnetic field line. And the reason why collisions are important is that in the F layer, it is free to do that. In the E layer, it is not because of the collisions. But right, if you want to simplify that equation, right, you can strip a bunch of terms out. You can come up with something which is called the ambipolar diffusion equation. And then we'll simplify it even more because, this still has too many terms for my liking. I'm fine with shoving a bunch of terms if the computer is solving it, but if I want to understand something, this is what physics is, right? You strip out as many terms as you can, and you linearize anything you can't strip out. So if you have some magnetic field line, right, the drift velocity of an ion along that magnetic field line, and we're only thinking about the direction parallel to the magnetic field line for this, is given by this equation. So we have a diffusion coefficient here, which again is Boltzmann's constant. You have the plasma temperature, you have the mass of the ion, and you have the collision frequency between it and the neutral species. And then you just have, a nice standard, you have a gradient term here of the density and a gradient term of the temperature and a term related to gravity. So what does this mean, right? And we can actually strip it down a little bit more before we really start worrying about it. So if we really want to, we can start getting rid of things. The gravity term really, electromagnetic forces are much stronger than gravitational ones, so we can get rid of that. Um, we can simplify things. If we introduce a plasma scale height here, right? So we were thinking earlier, way back at the beginning of the lecture, we were talking about the scale height in the thermosphere, right? Which is this pressure gradient force. We can come up with an analogous one for the plasma, right? The plasma in the upper F2 region in the top side decays very similarly because of this ambipolar diffusion to what a neutral gas would do, right? The plasma just follows a very similar shape. So what you end up getting is you get this nice equation when you make all these simplifications. The rate of change with height a lot or distance along your field line of an ion is 1 over the scale height and then 1 over this term related to the change in temperature with height. And you can imagine if we said, oh, well, we'll make the temperature constant, this term would go away and you have a very nice simple equation, 1 over, the derivative with respect to r is just this constant term, which is the scale height, right? Which just gives you that exponential profile. The thing that's important about it is that the scale height is double what the equivalent of the neutral atmosphere would be, right? So if you have oxygen, and the scale height of oxygen is 100 kilometers, the scale height of the oxygen ions would be 200 kilometers. And this is really easy to understand if we think about the characteristics of the plasma. So electrons are very light, right? And we talked about at the beginning, light things diffuse very quickly compared to the ions, which are much heavier. But when those electrons diffuse upwards, right, they're charged. They can't just do that freely, right? That creates a polarization electric field. And that polarization electric field then pulls the ions along with them, right? And it also arrests the electrons. So what ends up happening is that the effective mass of the ions gets cut in half because it's sort of the average between an ion and an electron, which basically weighs nothing. And so the ions diffuse as if they were half the weight that they actually are, which is exactly equivalent to saying the plasma scale height is twice that of the equivalent neutral species. So why does that matter? It means that the ions are going to diffuse away much more slowly than the neutral gas does. Right? And this is partially why when we talk about the plasmasphere and the magnetosphere, right, we have a big plasma content up there, even though there's not very many there's not neutral species up there, right? Because those neutral species are decaying away twice as fast as the ions. So you end up with ions, when you go high enough up, you have lots of ions now relative to neutrals. And that transition is quite high. It's generally outside the ionosphere, but that's still important to know, right? Of the lowest reaches of the ionosphere is so many neutrals compared to plasma. But then at some point, plasma is now dominant, and it's in a large part because of this ambipolar diffusion. So if we take all of these things together, right, and we say, okay, we have, this is something I did as part of my PhD research, just so that I could feel like I understood the ionosphere. Because there's just so many different things that it's hard to feel like you actually understand it sometimes. At least I find it is. That may not be true for all of you, but for me. So if you take all of this and you just throw it together, right, you have this ambipolar diffusion equation. You can find all of the collision rates, you can find all the reaction rates, you can do all the ionization calculations, and you can throw it into MATLAB and have it churn away and say, okay, make me an ionosphere. All right, so that's what this plot is the result of. Here we have the dashed black line is our electron density, and this is giving us this ionosphere profile that we're used to. You have your E layer, you have your F1 layer, you have your F2 layer. And we can see that we have different ions at different altitudes, right? In the E layer, your most dominant ion is O2, right? In the F2 layer, your most dominant ion is oxygen, right? Monoatomic oxygen. And your F1 layer, your most dominant ion is nitrous oxide, right? Which we haven't really talked about very much. Okay, why is this happening, right? Let's look at the photoionization rate down here. So we see, again, up here where the peak in ions are, 300 kilometers, there's very little ionization, right? There's basically nothing. Um, there is a little bit, but there's really not very much, right? The peak of ionization is down here at the F1 layer, and there's another little peak at the E layer. And so, right, our peak ion in the F1 layer is nitrous oxide, and our peak photoionization is nitrogen, right? So why is this happening? So if we look over here, I called it the recombination rate, but it's not exactly right. It's essentially just the reaction rate of different ions. So you can see that as soon as that nitrogen is being created, it's being lost, right? It is a nice big molecule. It's exchanging its charge with other species. And in particular, it's exchanging that with nitrous oxide. And nitrous oxide is a pretty rare species there, and it has a pretty long lifetime. So all of this nitrogen is getting ionized. The nitrous oxide isn't getting ionized at all. It's very transparent to the ultraviolet. It's getting converted into a nitrous oxide ion. And so the nitrous oxide ends up sticking around for a long time, right? Even though it's not being created from the photons, it's being created through these charge exchange reactions. And then it has the ability to diffuse upwards, but then it starts exchanging its charge with the monoatomic oxygen, and then that oxygen sticks around for a very long time, right? And as it drifts upwards, it's a lot lighter. It drifts upwards more quickly. It ends up being the bulk, right? Most of the ions here are monoatomic oxygen, even though we're really not producing very many of them. And most of the ones we are producing are much farther down. So this is why all these different parts start combining together to give us that shape that we're used to. The E region, though, is nice and well behaved, right? Most of the ions are O2. Most of the ionization is O2. Most of the loss is also O2, but it's in this photochemical equilibrium. We're making an ion, it's colliding right away, it's disappearing. Diffusion and all these other things aren't important down there, right? So generally, E region, diffusion doesn't matter. It's just ions are being created, ions are being destroyed. Very simple. The F2 layer, no ions are being created. Everything is diffusion. And you can assume with a pretty good margin of error that everything is oxygen, is just O. It's atomic oxygen. The F1 layer is the confusing one where diffusion is important, but it doesn't happen that quickly. It's a kind of a mess of all of these different things, right? And this is always true in all of science, is that whatever's in the middle is the most complicated part. But luckily, you only need to worry about the F1 layer in the daytime. So, yeah, at least you can rest at night. But what's really important, and this will come up for especially people studying, I think one of the groups is looking at gold or other kinds of instruments. One of the quantities that you get is the O to N2 ratio. And you can see why that matters here, right? N2 is determining that ionization rate, and O is determining everything else, right? So that ratio between O and N2 is a very strong indicator of what especially the F2 layer is doing. It's a very strong indicator of, F2 chemistry. If you had to boil all of this complexity down to just one ratio, one number, that's what that is. And that's why that'll matter. So in summary, right, the ionosphere is made of multiple ionized species, right? And the principal source of ionization from those is from, hard ultraviolet photons from the sun. So the lowest layers, the E and F1, are dominated by photoionization, and they're relatively easy to predict because, we can look at the solar cycle, we can look at sunspot number, we can look at F10.7, and we can know generally how much ionization to expect. The F2 layer, on the other hand, is diffusion dominated, right? As plasma diffuses up and down magnetic field lines through this ambipolar diffusion. And so it's much harder to predict, right? Because it depends on how the neutral wind is pushing those ions around. It depends on how the chemistry is changing. And all of this is coupled to the thermosphere. And as we'll see in the next lecture, the thermosphere is also coupled to the magnetosphere through the ionosphere. And it all becomes, we'll start talking more of those fun arrows and things on that picture at the beginning. And so that's what we'll talk about in the next lecture after we have a little break, are storms and the high latitude ionosphere and how that kind of throws a wrench into everything that we've just talked about. And I have these on, they're in both sets of slides, just some suggested reading. There are some great textbooks out there. In particular, the ones that were most helpful to me was Shunk and Nagy on ionospheres and Hunsucker and Hargreaves on the high latitude ionosphere in particular. But there are also great ones. Kelly's book is quite popular with our PhD students. Francis Chen for plasma physics things. Rishbith, Introduction to Ionospheric Physics is, it's from the 60s, it's quite old, but it's actually probably the best one for just, if you're not an ionospheric person, if you don't need to know all of the detail in Shunk and Nagy, Rishbith is very good for just giving a nice, a slightly lower level explanation. And then a bunch of other stuff to do with data assimilation. Yeah. I like those books, but they might not be relevant to you. Perfect. So I guess, should we do a quick break before we move into the next one?
Yeah. Thank you for the first part of your presentation, Dr. Ben. Everyone liked the talk.
Good.
I suggest 10 minutes break. Okay for everyone. 10 minutes. Is it too much? 5? So okay, let's take a break. Okay, we can come back in between 5 and 10 minutes.
Perfect. Gives me a chance to grab a coffee, right? So
Oh,
yeah, I
okay.
got to get more caffeinated. Yeah, the next one I'll have to move through quicker. So yeah, perfect. All right.
Perfect.
Do
So
it in 5.
see you guys. See you very soon.